Hello. Welcome to the next section in the Dr. Taylor's math channel for calculus. You should have seen section 1, limits, 5 videos, and there are also some breakdowns of details, but those 5 videos give you the general idea. Now we're going to take a look at limits and extend it into what's called the derivative. Specifically, we're going to look at what's called the difference quotient. I tried to make the lighting better. I don't know if it is or not, but this is the best I can do with what I've got. So let's take a look at some information. The value of a non-constant function may change every time x changes. In other words, if the line is not a constant, like y equals 2, which would be a flat horizontal line, then it has some slope or some curve. So as I change my x value, my y values at different x positions will be in different places. That's all this is saying. And there's an example of one, a crudely drawn curve. There's x1 and x2. x1 being an input that gives me out an f of x1 or a y1. x2 a second input that gives me f of x2 or y2 at a different output value. Just from those letters, x1, x2, y1, y2, you probably already have a notion of some of the formulas that might apply. Distance formula, midpoint formula, slope formula. We're going to look at some of those today. That change between my first input and my second input we will call delta x. Delta means change. They were using delta in the epsilon delta method to represent a small change as one x goes towards another when you're looking at a limit. We're sticking with that delta symbology, okay? So f of x1, f of x2, and of course, the derivative of a function is another function that equals the ratio of the change in x, where x is changed by a very small amount. What a mouthful of mathematics ease. What is it saying? What is a rate of change? Let's think about what a rate is. Rate is a sub-word of ratio or rational. Those all mean basically a fraction construct. Now there's a subtle difference between a ratio, a proportion, and a fraction, but they can all be expressed in fractional form. So this derivative of a function is another function, okay? So that curved function we're looking at now, that f of x, the derivative will be a different function, and we'll give it a different name. Instead of just choosing a different letter, what we generally do is we do f prime of x. That shows you that's the derivative of the original function f. So if you see 1 prime, it's the first derivative. If you see 2 primes, it's the second. If you see 3 primes, it's the third. We're going to focus on first derivatives. The higher order derivatives will be farther down in the series. All right, thus the derivative function equals the rate of change of that function, and that basically means rise over run. So what formula is that? Slope. All right, and the value of the derivative for an EX value is the slope of the tangent line to the graph. Now you know why it's a slope function. The slope of the tangent line. And what is tangent? If you remember from geometry, if I have a circle, right, and a line that just touches the circle in one place, that's called a point of tangency, which make that a tangent line. So you can imagine that a tangent line to a function touches the functional curve in just one place. And that's what we're looking at. And there's the tangent line at x1, right? If that was tangent at x2, I kept that same angle, it would go through there. It wouldn't be tangent, right? So what happens is when I go to a different input value, I'm going to have a different tangent line if my slope, if my function is non-constant as this is. So now you can see the blue one is from x1, f of x1, and the red line is for x2, f of x2. The line through point 1 and point 2, they're showing those two dots. So I am not quite tangent yet, right? Notice it said tangent and that didn't. But we want to make that red line a tangent, and when we do that, that will be the derivative. Now, the only way we can make that red line a tangent is right now it's something called a secant. A secant is like a circle with a continuous line that goes through it and touches it in 2 places, right? Instead of 1. So you can imagine a tangent line on a circle. If it got pushed down into the circle, then it would go through the circle and intersect in two places. The same thing's happening here. I'm intersecting at point 1 and point 2. So if I want that, if I were to make delta x smaller, you remember the epsilon delta formula for limit, if I squeeze it in the x, I should squeeze in the y, and I should get closer and closer to an output point. Well, if I squeeze this x closer to that, I'm squeezing f of x closer to that output point. It's the same type of thing. So what we're going to be doing basically is taking a limit as delta x goes to 0, because I'm squeezing these closer together, and when it approaches 0, that approaches the formula for the tangent line in its slope, rise over run. And there's the slope formula. M for slope equals y2 minus y1 over x2 minus x1. Now, this presentation is kind of long, and I will blast through a few of these slides, and you can look at them all. They're on my math-science.weebly.com website. All right? And they're the Smart Notebook files that are embedded in the links to the right of all the units. When you open them up, content that you're going to do homework on is on the left. Tutorials for that kind of homework is on the right. So we change y to f of x2 and y to y1 to f of x1. Realizing that f of x is the same thing as y is an output, f of x is an output. Why do we use functional notation? Because it lets us tell you what letter was the input letter in that functional statement to the right. So looking a little closer, we can make more modifications, right? So we look at these two things, right? And I notice that this I could say is x, and then this would be x plus delta x, right? So x2 could be x1 plus delta x, but if I only have one x, I could leave that one out in effect and just call that x and x plus delta x. So if that delta x was 2, that would be x, and that would be x plus 2. So if this x equaled a value of 4, then this x input would be a value of 4 plus 2, or 6. And as 4 gets closer to 6, that line, the blue line, gets closer to being the tangent at the output of the red. All right, so again, I just dropped the x1 for convenience, and now I can drop the f of x1 because now it's just f of x, and of course the x2 can be changed to x plus delta x, or that initial plus whatever distance I move to the right. That's all that's saying. It's really not that hard. It looks real complex, but it's not that hard. If I took 2 steps to the right, I would be at the other side of the smartboard. I'd be at f of x plus delta x. If I come back here, I'd be back at f of x. All right? So positionally, I think you can get that. So now we're going to adjust even further. We're going to adjust this statement to match these modifications. And now f2, I'm going to go back. f of x2 becomes f of x plus delta x. F of x1 becomes f of x, right? x2 becomes x plus delta x. That's how we described it. And x1 becomes x. Okay? And you're welcome to play with that all you want when you open the Smart Notebook up yourself. Now we have an equation for the line, the slope, it should say for the line, it is the line. Equation for the line between P1 and P2, but it's really not an equation for the line, is it? It's an equation for the slope of that line. And we'd need a y-intercept, we'd need a b, and I don't know where that is, and that's not important for derivative. So let's consider the following. If I want to make a tangent to point 1, which is x, f of x, that's what this is saying. Point 1 is the coordinate point x, and up f of x, the output value. So that tangent could be expressed as delta x gets smaller and smaller. What's going to happen is x is going to move, or delta x is going to move back towards x, actually, because if delta x gets smaller, then I'm getting closer to my original spot, right? As delta x approaches 0, x plus delta x approaches x plus nothing, right? And that would be x. So look what's happening as delta x gets smaller. I'm kind of doing this in a piecemeal fashion. You can see the output values changing. And as that output value changes, that red line would be moving. And as it moves back again and again, you can see that that red line now is not touching point 2 as it was before. So when I adjust that, we would see that it starts to tip down, right? Because it's following those lines. And there's some nice interactives I've linked at the website that lets you see that dynamically, not in stop motion. So now, let's move the derivative even closer and closer as this process unfolds, and you can see that eventually, when I adjust those lines, notice they're getting closer and closer to becoming what's called collinear. You might think of them as the same line, but it's really two lines that lie on top of one another exactly. So they're equivalent lines. They're not really the same line, they're equivalent lines. They go through the same plane with the same y-intercept and the same slope, so they lay on top of one another. That's called collinear. All right, so what's going to happen if delta x approaches 0? I think I gave that away. Boom, they are the same. And so what this is if you look at it, is if we took the limit of m as delta x approaches 0, we would come to that point with the epsilon delta formula. We would come to that point we cared about. And then that line would be going through that point would be the slope of that curve at that x value. Because again, if we went to a different x value, that slope would be drastically different. So realize it's a slope of a curve, but it's a slope of a curve at any input value, right? So it's not just like saying, oh, there's a slope, it's 3/2. No, now the slope is a variable. It varies depending on what you put in for x. And this is really the demarcation between what calculus is and what algebra is. Algebra will solve for a value of x at some discrete location, one single instance. X is 2, right? And 3 seconds later, if I solve that problem, x is still 2. But if I'm traveling along this line here, f of x is something, and 2 seconds later, it's something else. So the slope at f of x is something, and the slope at f of x plus delta x is something else. So what that means is calculus lets you find a myriad of solutions at that, and then you can find what's called the instantaneous solution. At time t now, what is that slope, as opposed to time t now, which was 4 seconds later. So this allows us to evaluate the dynamic. And since life is dynamic, that's why calculus is used to do so much of the physics and the things in life that are dynamic, and evaluate those. You're still using your algebra skills. It's like saying, well, I don't use Spanish if I talk about philosophy in Spanish. Absolutely you use Spanish, but it's no longer about Spanish, it's about philosophy. Absolutely we're using algebra, but it's no longer about algebra, it's about calculus. And the algebra is the language we're expressing this in. And the calculus is actually a shortcut for a lot of algebra that we wouldn't have to repeat over and over again. It gives us a greater, broader understanding of a dynamic, because a dynamic's more complicated, so we need something that helped us get our head around it. And that's what calculus provides. All right, so by using a limit, as I said, as delta x approaches 0, and you can see that statement up there now, that's very close to the difference quotient. But I see that, look, there's some simplification that can happen here. Up top, well, that's not f times, right? So I can't distribute, right? So there's no simplification here, but this isn't a functional notation, is it? This here is actually, I'm in the way of the thing, I'm sorry. This here is actually a statement that's not functional. It's just this and that minus that. So those parentheses are actually not necessary. Now, they gave us the y x2 minus x1 value, right? But they're not necessary for that. So I could simplify that bottom, and those parentheses could be dropped. And when I do that, I can say, hey, look, I'm going to skip through here. Okay. Before that, I'm sorry, I got ahead of the presentation. Before we simplify that, they're talking about some notations that you would need to know. I talked about f prime, right? Well, this is df dx. Well, if you think about this as change in y, delta f, delta x, there's delta x, right? So change in y over x, that d is the derivative of f with respect to x. The derivative is just another way of saying that I'm taking that limit of that change. That limit of that change. So that's df dx. That's another way you could see that, all right? With a little twist on that limit, okay, we can look at how it can be used, all right? And so now we're going to look at the simplification, and you can read through those yourself. There's no reason for me to read to you. But this is the d dx, the derivative with respect to x of f of x. That's the same thing as this. Also, big dx, that's the derivative with respect to x of f of x. Again, that's not multiplication. That big D sub x is telling you that's a derivative statement. Another way you might see it in the textbook, in the AP test, most certainly. Or d dx, the derivative with respect to x of y. Or finally, dy dx, which is what is the most common thing, when people will just say dy dx. That's really the derivative of y with respect to x, but dy dx is easier to say, and mathematicians like to simplify things, let's say. And the derivative with respect to x of y, okay? So that functional statement f of x is the same thing as the output variable y. So that's all the ways they could ask you the same thing as in typical math fashion. They're giving you a whole lot of different ways to say the same things, and you got to kind of distinguish between them because they're going to throw a lot of similar questions with different looking, similar things they want to see with different looking questions, I should say. And I want to eliminate that confusion right up front. Okay, so now I can insert this function into any one of these. Okay? So I could take the derivative of 5x cubed plus 3, the derivative of 5x cubed plus 3, the derivative of 5x cubed plus 3, or the derivative of 5x cubed plus 3, all of them with respect to x. That means that's the input variable I care about, the bottom one, the dx. That's the x variable. If there are any other variables that are not x, we're considering them constants. They are not part of the function of y. Y is a function of x. Okay? And then partial derivatives and things like that. At higher level calculus, you can deal with multivariables. All right, so I could write this as the derivative with respect to x of 5x cubed plus 3. All right? All of that can be, written the same way. So let's just, probably would be better if that was in parentheses, because it looks like the derivative of 5x cubed plus the discrete amount 3, right? I think parentheses around that would have been a better notation. So, the most common verbal expression is dy dx, as I said. Let's do an example problem. So we're going to find dy dx, or the derivative of y with respect to x, of the function y equals x squared. Okay? And we're going to put into, to find that, we're going to put into the difference quotient that x squared where it belongs, because that is the input, that is the actual function that's being evaluated as y, and x, as a variable, is the actual input value you're evaluating at. Okay? So let's look at that formula, and let's plug in what should go there. And if I were in front of you, I'd be asking these questions to you, but since I'm taping this for you, I'm going to uncover it more quickly. So, in the case of x squared, I'm going to put that in where it says x, because this is f of x. F of x is x squared. Could I not say that? Could I not say f of x equals x squared? Is that not the same thing? And if I did that, then x is the input variable, which means I put an x in everywhere I see an x, right? So that's kind of rudimentary, but as this becomes more complex, maybe with compound functions or whatever, that functional understanding is very important. So what am I putting in place of x? I'm putting in the x. But what am I going to put in place of x, the function of x? That's going to be slightly different. So let's look at how that unfolds. Notice this, though. Remember I said the parentheses? X plus this minus x. What's x minus x equal? You got it. It equals 0, which means that I can just replace the bottom with delta x. Now we're really looking like the difference quotient even more. So now I have x plus delta x quantity squared, that's y2, minus x squared, that's y1. Why is it squared? Because y is x squared. So when I put in the values, I got to square it. That's the outputs. That's the input, right? What's the input? X. So that's kosher, right? So now, continuing as delta x is approaching 0, what's going to happen to that fraction? You've done enough limits now. Plug in. As delta x approaches 0, what happens to that fraction? You got it. The fraction becomes a fraction over 0, which makes it undefined. Now, I don't know what the top evaluates. It could very well be indeterminate, 0 over 0, but it's at least something over 0, so it's undefined at least. And we know at undefined or indeterminate, we need to use alternative methods. We need to either divide out and cancel, right? We might need to expand and simplify. We might need to look at rationalization techniques, or finally a table if nothing else works. That's why we spent all that time working on limits, to understand how to get this. But we're going to show you, once you do this a few times, it can be tedious. There's a way around that tedium. Thank God for calculus. All right, so let's go ahead and do what it says to do. When I plug in, I get undefined. So let's see if we can simplify out. Okay, can I factor and cancel? I don't know. But I see I've got a binomial squared, don't I? Isn't that like x plus 2 squared? That means x plus 2 times itself. So couldn't I expand that out, that binomial squared? I absolutely can expand it out. So let's see what happens. This shift in the x direction, we remember from the 4 questions and from conic sections, we called that shift in the x direction h. Remember that? And we called the shift in the y direction k. So what's going to happen now is delta is a specialty thing, and I'm typing a textbook. I don't. The more specialty things I type in, the harder it is for typesetting, whatever. And now that we're doing things in computers, it's easier. But still, delta is not a simple keystroke on a normal keyboard. That's what it boils down to. Whereas H is a simple keystroke, and we know that H represents a shift in x. A shift in x is a change in the x direction, and delta means change, so delta x means change in x, so we're going to use h to represent that shift of x. So where's the h going to go? It's going to go everywhere you see a delta x. And voila. Now what we have is something that's very, very similar. But look, I still have delta x there, right? Don't forget, if this becomes an h, that can't stay delta x, otherwise there's nowhere to plug in the 0, right? So that's got to change to h approaches x. And what you're looking at now is the difference quotient. Okay? So now we've adjusted it up top, and you have what is now called the difference quotient. The difference quotient is basically defines a derivative. Okay? The difference quotient is basically defining what a derivative is, for all intents and purposes, practically speaking. All right. So now we plug in stuff, but before we plugged in that 0, it still not work. So we did x plus h squared, and we've got that. Now you should know that. You should understand that. And if you're watching this at home, and you're not part of Carnahan's class who had me last year, maybe you're not as fortunate as they were. But when I have a binomial squared, what that means is something, when I square something, it means something times itself, doesn't it? Okay? Now, when I do something times itself, that means I'm going to multiply this times that. But since there's more than one thing in both of those, I have to be fair. So if I imagine my multiplication of x, I have to not only multiply x by this first term, but I also want to distribute that x and multiply it by that second term as well. Now everything over there has been multiplied by x, but what has it not been multiplied by yet? That's right, y. So I'm also going to have to multiply. Notice that I circled not just h, but the plus in front of it, because what if it was a minus? It matters. The sign of that second term is very important. So h times that first term would be my third distribution, and of course I need to be equitable and distribute it into both as well. And the way I describe this kind of equity is like if I'm handing out dollars as you walk in the door, and if the last person walks in, I don't give them $1, I have not distributed that dollar equitably to all members of the group. I need to distribute that X equitably into all members and that H equitably into all members. It's very, very important. Now, the reason I did this with 1, 2, 3, 4, how many arrows are there? 4. That means there'll be 4 multiplications. If there's 4 multiplications, there will be 4 terms. Now, will terms combine or not? It depends, but there will initially be a term for every multiplication. 4 monomials, 4 terms that will make a polynomial a many-termed statement. So we can see that x times x is x squared, and x times h is positive xh. We can also see that h times x is positive hx, but since 2 times 3 is equal to 3 times 2, I would say hx is equal to xh. And I'm going to write them both as xh to make the obvious more obvious. Okay? And now finally, h times h is positive h squared. And we see clearly that, hey, there's 2 of those. There's 2 xh's, or in that case, I wrote it as hx. Does it matter? No, it does not, and I think you're savvy enough to get that. Okay? So that's a quick overview of how that happened. There's also a shortcut, and those of you who knew it, I could do Pascal's triangle, which you can see one of our document camera analysis to show Pascal's triangle. But look, the shortcut is square the first, square the last, and in the middle is the number that's the exponent times this term with its sign times that term with its sign. So x times h is xh times 2 is 2xh. Voila! X squared plus 2xh, or hx in this case, plus h squared. That is the shortcut. It only works for binomials. Don't fiddle around and try to do it. How many of you, if I'd have written x plus h, would have written x squared plus h squared and stopped? I know many of you would have. All right, maybe not in my class, but some of you I definitely think would have. I see that accident happen all the time, even with college students when I tutor them. It's just a reality. They forget about distribution. Be fair. Be equitable. Okay, so do you notice anything helpful? Now, just look at it, and then come back to me in a second. Okay, welcome back. If you've looked at that, you can see that there's an x squared in front and a minus x squared in back. The same way we got rid of the bottom x and x, negative x. Now we've got x squared and negative x squared that will also cancel, and that's sweet. I love when things cancel out. I'm great at adding 0 to stuff. I'm really good at it. I'm even better at multiplying stuff by 0. Man, I'm good at that. So, let's take a look at what's left on top when x minus x squared equals 0. They cancel out, and I'm left with just the 2xh plus h squared plus h. Now, if you did all those limits questions and those homeworks I asked you to do, you'll be jumping all over this. You'll have had this. You'll have figured it out. If you haven't, if you're sitting here like, what's he doing? You've ripped yourself off. You need to go back to the limit section and go back to those homework problems I assigned and do them. And look at the solutions manuals and understand how you divide and out and cancel. Understand how you factor out and divide. Understand that. That's a critical algebra skill. It's like trying to speak English without using any determiners, right, or conjunctions. I mean, you can't do that, not effectively. You need to understand the fullness of the language, the basic grammatical skills, and understanding how to factor and cancel is a basic algebra skill. So what do they all have in common? 2hx plus h squared plus h? Hopefully you've said h, and you'd be right. And then I would factor out that common h. You see it? And when I factor that out, remember it's like undistribution, yes? So I undistribute the h out in front of this. When I divide that by h, I'm left with 2x. When I divide that by h, I'm left with h to the 1. Now, h on bottom, it doesn't have to be factored out. But how many h's do you see down there? You better say 1, right? So what that means is that's really 1 times h. We just don't write that 1. Remember in elementary and middle school when you first learned how to do the variables and you wanted to write 1c or 1x, and they later said, you don't need that 1, honey, it's okay. That 1's still there. There's 1 of them. So could I factor h out of 1 times h? Yes. And I need to think of it that way because when I do that and I cancel these h's, I have to imagine that that 1, that's still down there. It doesn't turn into over nothing. If it was over nothing, it'd be undefined, right? And it's not undefined. It's over 1, which makes it a whole number value at very least, okay? So I want to think about how I simplify. It's very, very important, okay? So now when that cancels out, it's over 1, and look at that. Can I plug h into that function now and evaluate it? It's no longer going to be undefined because there's no rational part. Remember that? When I have a polynomial form, it pretty much always works. The only thing that can mess with me is a radical, and there's no radicals there, so I can't get in the imaginary. So if I don't get in the undefined or indeterminate, and I don't get in the imaginary, I'm getting real numbers. Now, of course, every real number is a complex number, a plus bi, with 0 imaginary units. But the point is, let's just focus on what's simple. I'm in real numbers. Okay? And so 2x plus 0 is 2x. So what is the derivative dy dx of x squared? It is 2x. Okay? Not that hard. Not that hard. All right? Let's do some more. This first one is a little long because it gives you a lot of examples. The rest of these tapes in this series will be quite a bit shorter. So don't freak out. If you want to take a break, here's a good place to stop, 30 minutes in. Stop it, take a break, get a drink of water, look at Facebook, then come back, get your head in the game, and keep going. So I'll wait for you to take that break. Whew! Took you forever to get back. Just teasing. It's 2 seconds for me, right? So I'm glad you got what you needed, and now you're back, and your head's in it, and you're ready to move forward. All right, essential questions. What does the shape y equals x squared graph, right? So when I say that, it means what shape is that graph? That's what I'm asking you. 4 questions. Is it even or odd? Even. Is it positive or negative? Positive. So it's based on a curve, and it's pointing up. How many curves? 2 minus 1 is 1 curve. Oh, it's a u pointed up. Where's hk? Well, is there anything added or subtracted to x that's being raised to a power? No. Is there anything added or subtracted behind that x squared? No. So hk is at 0, 0. So it's a parabola at 0, 0. It's y equals x squared. It's the parent function of all quadratic expressions. It's at the home location 0, 0 without x being stretched or squeezed with any number in front of it or flipped with any number in front of it. It's just the parent function. You should know that shape. What are your clues? Is there any shifting? I already covered all that with that description. So look at the exponent. I'm going to quickly blast through that, right? And you could look at that yourself by getting on the thing. And I also, on the website, by the way, I uploaded PDF versions. So if you don't have Smart Notebook, you don't have to. The PDF version is openable with any operating system. If there's any interactives, you'll lose those, but everything else display-wise will be there. Step by step, slide by slide, it will unfold itself to you. Please use them. Booyah! There it is, as we said, curve pointed up at 0, 0, average width. Okay? So now, let's do this one. And I'm going to ask you to do this one. Here's where I'm going to ask you to pause and give it a shot. Y equals 4x, right? So the function y is equal to 4 times whatever the input is. That's what it's saying. So y is f of x, right? So if f of x is 4 times x, what is f of x plus h going to be? What's going to be 4 times, parenthesis where the x would be, and I would put in what it said, f of x plus h, right? So that's the different input. That's the clue I'm going to give to you. All right, go. All right, so you thought about it, and I just wonder if you saw anything. I don't know if you did or not, but, well, we'll see. All right, now a challenge for you. A challenge. Use the definition of derivative to prove that the derivative of a constant function is 0. So I'm telling you something. I'm saying I'm proposing that the derivative of any constant is 0. And I'm asking you to use the derivative function to prove it. Okay, so let's plug it in and see. If y equals 7, find dy dx. All right, so take a minute. See if you can figure out how it plugs in and what it evaluates to and why. All right, and if you can write down underneath of it a few sentences about why it works the way it works, then you understand it. If you just say, look, at 0, I can tell, yeah, you can't tell. You've got to be able to explain why it is. Okay? It just feels right is not an explanation. It just looks right is not an explanation. Here's why it's right. That's what we need. Okay, go. And welcome back. So there's that 5 minutes again I keep forgetting about. All right, there's a slight dilemma here. Where is the x? All right? If we do this, this will only prove the rule for 7, and there is no x. What might we use to prove any constant? In other words, I could use 7, but what about 8 or 12 or pi? Isn't pi a constant? Or e? Isn't e a constant? Yes. What about 9.73625? What about 1,250,372.9? So we need something more general than a number. What could I use, I wonder? If you think back in limits, we used some letters to represent numbers that were an input, and one of the letters we resolved was we used a constant c. So that generic constant c, we're going to use it for the word constant. And then in calculus, when I see the letter c, oftentimes, I don't want to say always, because always and never are bad words to use in mathematics, but oftentimes what that c represents is a constant value of any constant value. They just don't know what it is. Think of it like the original variable that you thought of, except this isn't a variable. It's literally a constant. It's just we don't know which one it is. So we've used a variable to represent it. All right, so when you do y equals c, and I could have asked you to do it, and if you'd like to, pause now and try it. Okay, so if you paused and tried it, great. If not, here we go. So let's plug in. All right? So obviously I plug h into 0. That's not going to work. But look, what was f of x, right? F of x is c. What is f of x plus h? C. What is f of x plus anything? C. So basically f of x minus f of x is equal to c minus c over some number h, which we call the 0, right? But when I do this value, the input is, no matter what, is 0, right? So what happens is there is no need to evaluate the h being added to x, because since the output is never changing, the graph is a consistently flat line, right? Its value is the same no matter what. So its slope is the same as well. Its slope is what? 0. 0 rise over infinite run. Don't go up, go over 1. Don't go up, go over 1. Don't go up, go over 1. Well, that's a line, right? It's still rise over run. It still is. So don't let that, but it should be 0 over 0. No, because when I have a constant function, the change in the x input becomes irrelevant, whether it approaches 0 or not. The x input is the output, right? That's what it boils down to. The x input, I should say, not it is, doesn't affect the output. That's what it boils down to. All right, and here we go. Said all that. So there's a new thing. All right? So now, woo, look at that. Now it's a fraction. I know you love them. I know everybody loves fraction. Everybody say, yay, fractions, right? Woohoo! All right. So let's do the function 1 over x. I could think of that as x to the negative 1, right? I could rewrite that. This is x to the 1. If it flips up, it's 1x to the negative 1, right? Those rules of exponents. Again, your fundamental algebra skills. I need to know my basic properties. I need to know how to rationalize a denominator. I need to know how to use conjugate pairs. I need to know what my exponent rules, and I need to know my log rules. All right? And it'd be really good if I can use the 4 questions, or if I knew the basic functional shapes, but I could remind myself with the 4 questions. Very important. All right, so you try it. Good luck. This time, there's the 5 minutes. Go. Okay, welcome back. Let's see if what you did is what we did. All right, so again, I'm going to write the equation, and h is 0 is undefined. What is f of x? F of x is 1 over x. So what is f of x plus h? It's 1 over x plus h, right? This says whatever that letter is goes there. Well, if that letter is x plus h, it's an expression, then the expression goes there. That's functional notation, plain and simple. Don't overcomplicate it. So let's do the insertions, and lo and behold, there it is. Now I have a fraction minus a fraction, so I can simplify, except when I do a fraction minus a fraction, what do I need to do to simplify that? What do I need? What am I requiring? Yes, I'm requiring the ability to evaluate them simply, and that will require me to have a common denominator, right? Got to cut the pizza in the same amount of pieces if I want to compare how much we each get. So let's pick a value that works with x and x plus h. Now, x is in x plus h, but h is a plus. So this and that, it's not sufficient to say those are the same. This number, whatever it is, and that number, that's two different numbers. And let's say they were relatively prime, 3 and 5. What would your common denominator be if your denominator was 1/3 and 1/5? Right? Because 5 doesn't go into 3 and 3 doesn't go into 5. So what do? 5 times 3 is 15. So it's the same thing here. X times x plus h is going to be the common denominator. Okay? When they're relatively prime, I multiply them together, and I get x squared times hx, or x times x plus h. Either one of those are equivalent statements. So it might be beneficial to have them stay factored out. It might be beneficial to expand it. I don't know. So let's do some substitution, and I get 1 over x, because I had to multiply this by x, didn't I? What I do to the bottom, I've got to do to the top. It's only fair. So what is missing? Now that looks like the common denominator, right? And that's all we're doing. We're doing inspection. Oh, this doesn't look like that. It needs that x. And if I had to put that on bottom, I got to put it on top. Now what's missing on the second one over there? That's right. The x is there, but the x plus h is missing, so it goes bottom and top. So let's do that. All right. Now I can add those fractions. What's 1 times x? It's going to be x. What's 1 times that? Itself, right? So I'm going to simplify everything over the common denominator. Now I wrote it as x squared plus xh, or hx, but could I have left it like that? Yes. Just did that. Doesn't matter. You should be able to think through those things. That shouldn't boggle your mind. All right, so what is 1 minus 1x, or 1x minus 1x minus 1x, because this gets distributed, right? Don't forget that this distribution must include the negative sign, right? Sorry about that rotation. So let's go ahead and look at it after it's been distributed. I've got x minus h. You can clearly see now that x minus x is going to add up to 0 when it combines. So I'm left with minus h over x squared plus hx. So now I have a fraction divided by a whole number. But every whole number could be expressed as a fraction. How do you do that? That's right. You put a 1 under that fraction, that whole number. Why did I do that? I did that because I want a fraction divided by a fraction, because then I can use my elementary school algorithm. Keep, change, flip, right? I hate those. But the notion is, it's this divided by that, and I'm always going to flip that. Never this. So this divided by that means that gets flipped, and that becomes multiplication. Multiplying by its reciprocal. Now, when I multiply fractions, I can just multiply straight across the top, straight across the bottom, and then simplify. Sometimes I can, now I don't want to ever hear the word cross cancel. That is not a word. There's no such thing. I can cancel, I can multiply, I can cross multiply. Those are all different things, and the words cross multiply are rarely used, okay, in my room. Canceling is used, simplification is used. All right, so I'm going to multiply. I'm not going to cross multiply. I'm going to cancel. If I cancel, I'm not going to cross cancel. So let's take a look at this. So we can see that we can cancel top and bottom because there's two h's. Except this is a positive h, and that's a what? Negative h. And remember, when I cancel that, that's really times 1, right? H times 1. It doesn't go away. It becomes a 1. And so this is the opposite of 1, which is negative 1. Negative 1 times 1 is negative 1, right? So, and 1 times the bottom is the bottom. So this times 1, it doesn't change it, right? That's basically what happens. So there is my simplified thing. Can I put h in as 0 now? Yeah, because even though that second term goes to 0, the first term has no h in it, right? So the first term doesn't go to 0. So that means the bottom is no longer all 0, which means it's no longer undefined, which means I can now actually do that simplification and achieve an answer. Negative 1 over x squared. Okay? So, can we write the initial equation in such a way that it makes taking the derivative easier? And I think we can. How do we say we could write that? As x to the negative 1, right? And if we wrote it as x to the negative 1 and tried it, you'd find you'd end up having to flip that thing back and forth anyway. So it's a wash, and I'm not going to focus on it. Okay? And there it is. See what I ended up having to do? I ended up having to flip this and flip it, and I'm back to the beginning. So it really wasn't a simplification that made any sense to me now. But in some other cases it does, and that's why I wanted to mention it here while we were talking about it right up front. Sometimes it's worth doing, sometimes it's not, and you have to be practicing enough to be savvy to know when. Sometimes I block this way, sometimes that, and I have to spar enough to know which way is the right time in that particular instance of time. Or the right way, I should say. Okay? So there is a worksheet, and here's some questions that students had. I'm going to end right here, and I'm going to say go to the homework that's here at the end of this video and do them, okay? And good luck, and I'll see you on video 2.